Hello again. We are going to learn in this lesson how to find real zeros of polynomials using a variety of techniques. I'm not going to lie, this section can get kind of hairy. There's a lot of techniques, but just remember that the goal is to use a combination of the techniques to maximize your efficiency in finding zeros. Again, our quest in this lesson is to find zeros, find zeros, find zeros, and not only just zeros, but to find real zeros. So our first technique is the rational zero test. You might remember this from Algebra 2, but I'm just going to go briefly through each technique, and then we will go into more detail on how you can use those techniques to find zeros of polynomial functions. So the first technique or tool that we have is the rational zero test. The rational zero test is interesting because it does not tell us what the zeros are. It only tells us what the zeros could be. That's why it says possible here, underlined like a bunch of times. These are the possible rational zeros. This is telling us that if this polynomial is to have a rational zero, and again, rational can be replaced with the word fractional for ease. It basically means that if this polynomial has a zero that is a fraction, or can be written as a fraction, that this test will generate a list of the possible. So again, not saying that they're all going to be zeros, but they are possible. Doesn't really make us sound really happy here, but let's just see how this works. So what we do is we have our polynomial. You want to make sure that it's in standard form, that the leading term is first, and so on and so forth. So we've got 3, 2, 1, none going here. So we're okay and good with that. So we're going to generate a list of possible rational zeros. We take the factors of the constant term, which in this case is 6, and divide it by the factors of the leading coefficient, which is 2. So what we do is we will translate this to all the factors of 6, which can include negative factors. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Those are all of the factors of 6. Then you want to do all of the factors of 2, which would be in this case plus or minus 1, plus or minus 2. And we're still not done. We need to now simplify these would-be rational numbers here. So to do that, we will now have 1 divided by 2, which is 1/2. 1 divided by 1, which is plus or minus 1. Then we move on to the next number, and that's 2. So we'll go with 2 divided by 2, which is 1. So we already have that. And then we'll go 2 divided by 1, which is plus or minus 2. Then we'll go to 3 divided by 2, which is 3/2, and 3 divided by 1, which is plus or minus 3. And then lastly, we'll take 6 divided by 2, which is 3, it's already in my list, and 6 divided by 1, which is plus or minus 6. So now we have generated our list of possible rational zeros. Now we are not trying to say that 2, 4, 6, 8, 10, 12 numbers are all zeros of this cubic function. What we are saying is that if this cubic is to have a rational zero, it needs to be in this list. So if someone said to you, oh, I think maybe 5 is a rational zero, that would be bogus because 5 is not in this list. It is a rational number that is not in that list. So just wanted to show you real quick how you use the rational zero test to find or generate your list. So right now, for this particular polynomial, we have 12 options, 2, 4, 6, 8, 10, 12. 12 options, or we can call them candidates. They are candidates for rational zeros. We don't know yet if they're actually going to be a zero, but we could do some synthetic division and find out if in fact these candidates are in fact zeros. Right now we're not going to do that in the interest of time, but I will show you again how to do that when we get to the end where we put it all together. Right now I just want to go over the 3 different tools that we have to find zeros, and that was the first, possible rational zeros. We use that guy to give us a starting point. So another tool that we have for finding zeros is Descartes' rule of signs. René Descartes coined this little test here, Descartes' rule of signs. And when you first read this, it's going to sound kind of weird, but hopefully once we do an example, it might make more sense. So Descartes' rule of signs basically says that the number of positive real zeros is equal to or less than the number of sign changes by an even whole number. Sign changes of what, you might ask? Sign changes of p of x. We can even put p of x in there. So I have down here, that sounds really wordy. I know it sounds kind of weird, but let's go to an example here. I have a polynomial here, p of x equals 3x to the 6th plus 4x to the 5th plus 3x cubed minus x minus 3. And what we are talking about here is how many times does the polynomial change signs. In other words, this term is positive, this term is positive. There was no sign change there. This term is positive, this term is positive, no sign change. This term is positive, this term is negative. That's one sign change. And now we go from negative to this negative term to this negative term, no sign change. So in this polynomial, there was one sign change. Okay? So that means that number of sign changes, 1. Alright, so now if we go back and we read what the Descartes rule of signs is basically telling us, is that the number of positive real zeros is going to be equal to the number of sign changes. So if it was equal to, that would mean that this polynomial could potentially have one positive real zero. And that goes back to my list from earlier where we were doing in the last example with the rational zero test. If we bring that back real quick, this polynomial changes sign from positive to negative, that's one sign change, and then from negative to positive, that's 2 sign changes. That means that this particular polynomial has 2 sign changes, and it's possible that this polynomial would have 2 positive real zeros, okay, because it has 2 sign changes. So that's kind of clarifying what we mean by sign changes. So back to this, we have that it's not just equal to the number of sign changes, it says or. So it is equal to or less than the number of sign changes. So it's either equal to 1 or less than 1 by an even whole number. Okay? If I just subtracted an even whole number, the smallest even whole number is 2. So if I subtracted 2 from 1, that would be negative. So in this case, I can't subtract an even whole number from 1 and get another positive integer. So that means that in this case, this particular polynomial can only have one positive real zero. It cannot have more than that. That's interesting because depending on how many zeros we have in our candidate list, we can now eliminate several. If I find one positive zero, then I don't need to test other positive zeros because I know that it's only possible to have one. So that's kind of how we're going to use that later to help us find zeros. But right now I just want to clarify again, let's suppose that there were 5 sign changes. That's not the case right now, but let's just pretend that we had 5 sign changes. What would that mean? It would mean that I could have 5 possible positive real zeros, okay? Positive real zeros equal to 5, or it could be less than 5 by an even whole number. So 5 minus 2 would be 3. 3 minus 2 would be 1. 1 minus 2, we're now into negative realm, doesn't work. So what we are saying is that according to Descartes' rule of signs, a polynomial that has 5 sign changes means that I can have 5 positive real zeros, or 3 positive real zeros, or 1 positive real zeros. I cannot have 2 positive real zeros. It has to be 5, 3, or 1. That is what Descartes' rule of signs is telling us. And in a similar fashion, we have the second part to his rule of signs, which is the number of negative real zeros is equal to or less than the number of sign changes, not for the polynomial, but you can see here for p of negative x. So before I can apply this test, I have to find what p of negative x is, which means I'm going to replace all of my x's with negative x's and then simplify my result. So negative x for that, negative x for that, negative x for that, negative x for that. So here we go. If I were to simplify this, a negative x to an even power is going to stay positive. So 3x to the 6th. A negative x to the 5th power, which is odd, is going to stay negative. So negative 4x to the 5th. Negative x to the 3rd power will stay negative. So negative 3x cubed. Negative negative makes this positive, and minus, positive x, and minus 3. Now, this is a different polynomial from p of x. So we have to calculate the number of sign changes all over again. So in this case, I have positive to negative. That's one sign change. Negative to negative, no sign change. Negative to positive, sign change. Positive to negative, sign change. There are 3 sign changes in p of negative x. 3. So going back to what the rule of signs says for negative zeros, it says that the number of negative real zeros is equal to, in this case, it could be equal to 3, because that's how many sign changes there were. It could be equal to 3. Or it could be less than 3, but by an even number. So less 2 would be 1 is an option. But if I subtract 2 from 1, again, I'm back into negative world. So we are sticking with, it can either be 3 negative real zeros or 1 negative real zero. Again, it is not possible to have 0 negative real zeros. So this is telling me that I have to have at least 1 negative 0. I have to have at least, in the previous case, at least 1 positive 0. That is what Descartes' rule of sign is telling us. So again, just wanted to show you how to apply the test. Again, we'll see that tool used again later when we put everything together. So there is Descartes' rule of signs. Now, we go to our last tool that we'll be using, and that is the upper bound and lower bound. So we saw in the first example with the rational zero test that it is possible for us to have a lot of candidates. And of course, our goal is to start eliminating some of those candidates and narrowing down the possibilities so that we don't have to do a lot of work. And that's where the upper bound and lower bound can come in handy. All right, so I have kind of paraphrased here what the upper bound and lower bound are. The upper bound says that if you divide, and again, we're going to use synthetic division. So if you're dividing by negative b, or x minus b, so you can see here the x minus b, with synthetic division, I want to point out that when you're doing this, b is greater than 0. Okay? And in the other case, for the lower bound, x is less than 0. So x, sorry, not x, a. A is negative in the lower bound case, and it is positive in the upper bound case. But what we are trying to do here is bound. Bound means boundary. We have so many candidates that we would like to know if I try a number, do I have to keep trying numbers that are larger, smaller? You know, where do I go with this? So again, the goal here is to narrow down my list of candidates. So we have these upper bound and lower bound. So what this means is that if you divide with synthetic division, and if the last row of your, when you divide, the row that includes the quotient and the remainder, if that row has all positive entries, then we know that that value of b is an upper bound. And if it's an upper bound, we don't try any numbers beyond that number. And same is true for the lower bound. In the lower bound case, after synthetic division, if the last row contains alternating signs, then we know that that number A is a lower bound, which means I don't try any numbers lower than it. So it narrows down my list. So again, I will show you how that comes into play when we put it all together. But right now, I just want to show you a sample problem you might have on your homework. Here it goes. Show that all the real zeros of the polynomial are between -3 and 2. What this is really saying is they want to know, is -3 a lower bound and is +2 an upper bound? Because if this was an upper bound, then all of the zeros that this polynomial has would be smaller than 2. And if in fact -3 is a lower bound, it means that all of the zeros that this polynomial has would be bigger than -3. Okay? So to show how this upper bound, lower bound works, we use synthetic division. So I will make my elongated L that we learned earlier, or in the last section, and I will put all my coefficients. 1, I need a 0 in here, sorry about that, we need a big 0 here. And the reason why we need a 0 is because we are missing a cubic term, and when we're missing terms, we put a placeholder. So we have x to the 4th, no x cubed, -3x squared, 2x, so 4, 3, 2, 1, none. 4, 3, 2, 1, none. There we go. Okay, and for the lower bound, I am dividing by -3 and bring down my 1. And if you remember from the last lesson, we multiply diagonally and add vertically. So -3 times -3 is 9, 9 minus 3 is 6. This becomes -18. This is -16. Negative times negative is positive. What is 16 times, let's see here, 43. What number goes here? Not 43, I'm getting ahead of myself here. We're going to put 48. -16 times -3 is positive 48. And 48 minus 5 is the 43 that I was talking about earlier. Okay? So now, notice that for the lower bound, I'll pull this down again. For the lower bound, we have to be using synthetic division with a negative number. See, a is less than 0. So in this case, my a is -3. That's a negative number. It's less than 0. So my lower bound can apply. And after synthetic division, the last row, that's this row right here. That's the row that we're looking at. Sorry, I'll pull that up so you can see it. This last row right here. We look at that row, and we are looking for the numbers, the entries in that row to be alternating sign. So we've got a positive, a negative, a positive, a negative, a positive. That's alternating sign. That tells us that -3 is in fact a lower bound. Likewise, we can use the same system, and this time we're checking the upper bound. So we're going to go 1, 0, -3, 2, -5. And this time we're going to try the 2 to see if 2 is an upper bound. So I bring my 1 down, multiply diagonally, add vertically. Eight minus 5 is 3. So we get 1, 2, 1, 4, 3. Again, we are looking at the last row here, the row that contains the quotient and the remainder. Okay? In that row, all of those entries are positive. And because all the entries are positive, according to the upper bound, we have to be dividing by a positive number, and 2 is in fact a positive number, and we got a row of all positive entries in the last row. So now we know that 2 is definitely an upper bound, and therefore we have shown that all the zeros of this polynomial do in fact lie between -3 and 2. So that takes care of our tools. We have, to recap, the rational zero test. We have the Descartes rule of signs, and we have now the upper and lower bound rules. Now the last thing we want to do is I just want to briefly show you how we can put all of this together to help us with our end goal that we started with, was find the zeros. In this case, it says factor the polynomial. I can factor the polynomial if I know all the zeros. So that's going to be my approach to this problem, is can I find all the zeros? using all of the information that we have available to us, we are going to attempt to do that right now. All right, so we're going to start off with the rational zero test because we need a list of candidates. Otherwise, where do we start? We have nowhere to start. So we start by listing our possible candidates. Here's my crazy polynomial. It's x to the 5th power. So we are in for a whirlwind here of a problem, but hopefully you can bear with me there. So if you recall, the rational zero test takes the factors of the constant term, which in this case is 9, and we divide that by the factors of the leading coefficient, which is 2. So we are going to take all the factors of 9, plus or minus 1, plus or minus 3, plus or minus 9, and divide it by all of the factors of 2, plus or minus 1, plus or minus 2. Then we have to simplify all these values, and that can get kind of crazy. It's a little bit of a doozy. Let's see if we can do this. So I will go 1 divided by 2. You want to have them in order. 1 divided by 1. And now I'm done with the 1. Then I go to the 3, and I go 3 divided by 2. 3 divided by 1. And I'm done with the 3. Then I go 9 divided by 2. And 9 divided by 1. And now I'm done with the 9. So, at the end of the day, I have 2, 4, 6, 8, 10, 12 candidates. Now, I don't know about you, but I'm pretty confident that most of us do not want to use synthetic division 12 times to determine what the zeros of this polynomial are. That would just take forever, and that is not my intention at all, so please do not go home and try to do synthetic division 12 times. We want to use the tools that we have available to us to narrow this list. We want to narrow it down, shorten the list. So, one of the things that we want to do first is we will attempt to do some synthetic division because synthetic division will help us find maybe upper or lower bounds. We need to be paying attention to all these different things. All right, so here we go. I'm going to start, and I suggest you do the same. Start with positives and start with the smallest number. That's why it's helpful to have the list in order. So you start with the smallest ones because generally the zeros will be the smaller values. We hardly ever have to get all the way down to the larger values, and those are harder to work with anyway. So let's start with the lowest or smallest positive one, and I am going to have a 2. So we got 5, 4, 3, 2, 1, none. So we got 2, 5, negative 8, negative 14, 6, and 9. It's a doozy, I'm telling you. So we're going to start off with 1/2. So I bring my 2 down. 2 times 1/2 is 1. 5 plus 1 is 6. 6 times 1/2 is 3. Negative 8 plus 3 is negative 5. Negative 5 times 1/2 is negative 5 halves. And negative 5 halves plus negative 14 is negative 33 halves. And again, if you don't believe me, you can check your calculadoras. Negative 33 halves times 1/2 will give us negative 33 over 4. And a positive 6 and a negative 33 over 4 is negative 9/4. And negative 9/4 times 1/2 is negative 9/8. And a positive 9 and a negative 9/8 is 63/8. I know you hate fractions, but that's what you have your calculator for. So, first of all, is 1/2 a 0? No. Why? Because we did not get a 0 remainder. So we have now eliminated 1/2 as a possibility. Okay, so the next smallest positive 0 that we have at our disposal here is positive 1. So yet again, we will do some division. Put a 1 out here. 2, 5, negative 8, negative 14, 6, 9. Don't worry. I know you're probably already all scared, but I'm not going to do this 12 times, I promise. So, here we go. We get 2 times 1 is 2, 5 plus 2 is 7, 7 times 1 is 7, 7 minus 8 is negative 1, negative 1 times 1 is negative 1, negative 14 minus 1 is negative 15, negative 15 times 1 is negative 15, negative 15 plus 6 is negative 9, negative times 1 is negative 9, so you get 0. Yay, see, I told you. So at this point, we have that 1 worked. Okay, so we got a 0 remainder. So far, if I were to try to factor it right now, because 1 is a 0, if x equals 1 is a 0, then that means that x minus 1 is a factor. And I can take x minus 1, and if you remember from 3.3, these numbers are the coefficients of the quotient. So that's going to be 2, and it's 1 degree less than what I started with. I started with x to the 5th, so this is going to be 2x to the 4th plus 7x cubed minus x squared minus 15x minus 9. And what's interesting about this guy is that I've only found 1 0 so far. There's got to be more. And now I'm looking at this polynomial that remains, and I'm thinking to myself, here we go all over again. We have to generate a new list of possible zeros and blah, blah, blah. But what you should notice right now is that the constant and the leading coefficient of the remaining polynomial here are the same as the constant and the leading coefficient, minus this is a positive versus a negative. So even if I generated a new list, it would be the same list. That's good. So we don't have to do it all over again. We can use the same list to start generating more zeros for the remaining polynomial. So now what I'm going to do is I'm going to take this new polynomial, which is 2, 7, negative 1, negative 15, negative 9. All right? So those are the coefficients of the new polynomial, the resulting polynomial. And I'm going to go back to my list. And I know that 1/2 was already a no-go. So I'm going to try 1 again. Because 1 worked last time. You never know. It could be a double 0. So I'm going to try 1 again. And I get 1 times 2 is 2, 7 plus 2 is 9, 9 times 1 is 9, 9 minus 1 is 8, 8 times 1 is 8, and negative 15 plus 8 is negative 7, and that's going to give negative 7, and then negative 9 and negative 7 is going to be negative 16, and too bad, so sad, it's not going to be a double 0 because I did not get a 0 remainder this time. Alright, so now the 1 is out, and now I'm going to go to the next biggest number. And again, if you look back at your list, I'll bring it up here again. We tried the 1/2, tried the 1, the next one is 3/2. So we're going to try 3/2. By the way, thus far, we have not seen any lower or upper bounds. If I bring up the previous synthetic division, when we did the 1/2, we do not have alternating signs. This is positive, positive, negative, 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 positive. Those are not alternating, okay? And it's also not all positive. So if we're dividing by a positive number, then if you remember the lower or the upper bound rule, you have to divide by a positive number, which we did, but the row has to be all positives, and this has negatives in it, this has negatives in it. So thus far we have not seen any number that is a upper bound. But it would be nice to find an upper bound, and that might just happen for us in the next step. So 1 didn't work, but as we just saw, the next biggest number is 3/2. So we'll do this one more time and hope for the best. 2, 7, negative 1, negative 15, negative 9. 2 times 3/2 is 6/2, which is 3, and 7 plus 3 is 10, and 10 times 3/2 is 15, and 15 minus 1 is 14, and 14 times 3/2 is 21, and 21 minus 15 is 6, and 6 times 3 halves is positive 9, and yay, we got a 0. See how that worked? We got a 0, but beyond that, we're dividing by a positive number, and the last row is all positives. That tells us that 3 halves is an upper bound. There is no need for us to look for any more zeros that are bigger than 3 halves. Now, isn't that nice? Because that eliminates 9 halves, and it eliminates 3, and it eliminates 9. So we just got rid of 3 candidates that will not work for us because we see that 3 halves is in fact an upper bound. So now we have, let's recap what we have so far. Earlier we had that x minus 1 was a factor. Now we have that x minus 3 halves is also a factor from this 0 that we just found. And what is left? Remember, 1 degree less. This polynomial was a 4th degree, so now we are at a cubic. 2x cubed plus 10x squared plus 14x plus 6. Now we're at a cubic. All right? So I'm getting there. I've got 2 of my factors already. I feel like I still need some more over here because a cubic is still pretty large to leave like that. You'd want to try to get down to linear if at all possible. Okay, so now we want to try a couple of things. Right now that we're at a cubic, I want to talk a little bit about Descartes' rule of signs. Because now this is our polynomial that we're trying to factor now. It's 2x cubed plus 10x squared plus 14x plus 6. Okay? So what this is telling me is that let's generate a new list. If we went, well, first of all, these are all factors of 2. Let's just take out a 2. That would give me x cubed plus 5x squared plus 7x plus 3. All right, so now I can bring this to, we'll just do this for now. We can fix that later. Okay, because technically this 2 could be in the front if you wanted to. But for now, we factor out the 2. And now I'm looking at this polynomial, and I am noticing that there are no sign changes here. Positive, 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 positive. There are no sign changes here. So because there are no sign changes, that means that there is no positive real 0. No positive real 0 for this particular polynomial. So what are the possible rational zeros? Again, I am going to use the constant term, which is 3, divided by the coefficient of the leading term, which is right here. And there's nothing there, so we assume there's a 1. And this is really easy because 3 is a prime number. So the only factors of 3 are 1 and itself. So we only have 4 possible candidates for this cubic. And I just said that because of the rule of signs, there are no positive zeros for this particular polynomial. So there's no reason for us to try 1 or 3. So that reduces our list to -1 and -3. Now, that seems a lot more doable. So we are going to do yet again our synthetic division and see which of those 2 is in fact the winner here. So we're going to take and put -1 out here, and the coefficients of this polynomial are 1x cubed, 5x squared, 7x, 3, 2, 1, none, and 3. So 1 times -1, -1, 5 minus 1 is 4, 4 times -1, -4, 7 minus 4 is 3. It's looking really good. 3 times -1 is -3. Bam. 0 is our answer. So now we found yet another 0 using Descartes' rule of signs to eliminate those positive options. So at this point we can recap all the factors that we found so far. We know that 2 is a factor because we factored it out earlier. We know x minus 1. We found that earlier. We know x minus 3 halves because we found that earlier. And now I have another x minus 1 because it was a 0 yet again. Or sorry, it's an x plus 1, I'm lying. That's an x plus 1 there, sorry. Because you always do the opposite, so this is a negative 1, so this will be a positive 1. So I've got 2, I've got x minus 1, I've got x plus 1, and we have an x plus 3, or sorry, minus 3. Okay, so that's actually good there. And now we have what's left, this right here. 1 degree less. We started with the cubic. This is going to be a quadratic. 1x squared plus 4x plus 3. And we're almost there. But you already know that there are other ways to factor quadratics. We don't have to keep doing division anymore. We can now factor this using our previous methods. So we can do this guy, 1 and 1, 3 and 1. If I go 3 plus 1, that's 4, and that's the middle term. So this quadratic factors nicely to x plus 3 and x plus 1. So at the very, very end, we can finally completely factor this polynomial. We had the 2. We have x minus 1. We have x minus 3 halves. We have x plus 1 twice. We have it here, we have it there. So it's squared. And we have x plus 3. Finally, 10,000 years later, we have our factored polynomial. I promise you that not all your problems will be this long, but I did want to show you a problem that encompassed all of our tools. We used the rational zero test. We used, I keep saying Rene, but Descartes. His name is Rene Descartes. Descartes' rule of signs. We use the upper and lower bound theorems to narrow our list down and finally factor this crazy polynomial. Again, not all your problems will be that complicated, but I hope that you can rewind as many times as you need to understand the concepts. Good luck.